We made it. It's Friday. We're almost there. So close. So I said there could be some, let me just say that I know I have a lot of students, but I don't think all of you are mine. That's kind of what I'm thinking right now. I see some faces that I just know I've never seen that face in my life. All right. So 10 o'clock is fun. So this, I'm guessing, will be fun too. So I said that there was a competition. I pit you against 10 o'clock to see who can give me the highest 2-hour response rate. And so I just updated these like 3 minutes ago. So let's see what it is. So this section, the 11 o'clock session, has given me an eval rate of 76.13, which I think is really, really impressive. So thank you. Yay! All right, but nobody cares about that. You just care about did you beat 10 o'clock. And so the answer to that question is... Okay, so we'll get rid of this 10 o'clock. Actually, the one that I blew up for them, it didn't say first place or second place. I promise you it said last place. Just FYI, if you ever need matches, WAV has the best matches. I know that's random, but I think everyone in this department would tell you. Alright, so this is the first place, right? Yeah. Okay. And so this is gonna go boom, so if you have sensitive ears, you know. I did more on the 10 o'clock. Wait till she stops walking up the steps. Kudos if you're able to actually capture this. This is a fast reaction. Okay, we're ready. So it's blowout, I guess. What do you think's in my thermos? It's coffee because I'm a professional and it's been coffee all semesters. So let's see. We need to talk a few things, I guess, before we call it a wraps on the semester. So the exam is when? Tuesday. It is Tuesday. What time? 7 p.m. to 10 p.m. We got an evening exam. You guys like evening exam? Yes. I didn't schedule it, so get mad at the school, not me. I do what they say. So the exam is about twice the length of a midterm, which isn't really that bad because how much time do you have? You've got 3 hours, so this thing will be designed such that you can do the exam in 2 hours, and then you can sit there for the 3rd hour and second guess yourself as much as you want. Eventually just turn it in and forget about it. So, yeah. Where is it going to be? Where will the exam be? So I have, I went crazy on booking rooms. I booked like the 4 biggest rooms I could get. I think we're only going to use 3. So I think that we're actually not in this room, which I don't know why I couldn't get this room. So we're going to be in Andrews, so whichever the lecture hall is in Andrews, I think. We'll be in the big, small lecture hall. And then we will also be in Millington. I know. So I'm going to find 3 proctors so that I can float around during the exam. So you'll all have a proctor's. Good chance you might have seen them TAing lab or something. I don't know who it is yet, but we'll get that sorted out. So, final is Tuesday evening in one of those 3 rooms. I'll get room assignments out. I have a quick office hour right after class today. I figured it was best to maybe get that over with if you have some questions. So we're going to do that right at 12 in 2018. And then Sunday there's a workshop, and so Sunday is going to be the official final exam workshop. And so you guys can have me, as long as you want me, I guess. So we'll start at 1, and nominally we'll say 3 o'clock it ends, and we'll see. If you have more questions, I'm not gonna leave you hanging. So we'll hang out here as long as possible. That'll be in this room. And then Monday, I don't have anything scheduled yet, but the exam will be written by then, and I should be able to potentially put together some sort of office hour scenario. I've got to figure out how to make that work with 300 people. It'll be a nightmare. So I'm brainstorming some ideas there. I might just grab a conference room for a couple of hours and just hang out, and you guys can filter in and out as you please if you have questions. In that case, I might even do like an hour in the morning, an hour in the afternoon in case you have an exam on Monday. Probably not going to do anything Tuesday because, that would be scary for me. Okay, and then I'll do my best answering emails over the weekend, etc. Okay, so let's see. Let's get rolling. We've got about half an hour of lecture. Any other questions about final schedule, other stuff? Okay, so last time, where did we end off? And we're gonna blow up that other balloon too. It's also hydrogen, so we'll save that for when it gets boring. Never gets boring in here, Professor Watt. Okay, so reviewing from last time, we found, and this is actually cool. So last time we ended with actually somewhat becoming organic chemists. And so what we can do is we can take a terminal alkyne, and we found that the acidity of that terminal proton is pretty acidic. So we found that the pKa is around 25. That's a lot more acidic than an sp2 or an sp3ch bond. So what we're able to do is take advantage of that by taking our terminal alkyne, reacting it with a strong base. And so what we end up with is a deprotonated terminal alkyne, which can then act as a good nucleophile. Okay, so once we have our good nucleophile, we can react it with a primary alkyl halide. And it can only be a primary alkyl halide, because what if it were a secondary alkyl halide? What's the first question we ask ourselves? We ask, is it a strong base? And so, is this a strong base? Sure, its conjugate is definitely with a pKa of 11. And so with a secondary alkyl halide, we're probably going to go E2. But with a primary alkyl halide, we can take advantage of the nucleophilicity. And so you can see we're able to form new carbon-carbon bonds, which for a lot of organic research is kind of the point. All right, so we'll move on today. I just wanted to add, so in your notes, before we even knew what elimination was or that it could even take place, we saw some examples where we'd say, all right, this secondary alkyl halide will react with sodium methoxide, and all we really knew is it could do SN1 or SN2. Now, we knew it was a charged oxygen, it was a good nucleophile, and that it could do SN2, but that's changed a little bit. We have more information. We have to consider some other things. And so now we wouldn't say this goes SN2. We know that the basicity is going to dominate to go E2. So if you go back and we're comparing SN1, SN2 reactions and examples in your notes, you now need to keep in mind that there's also E2 or E1 that could be taking place. So we've gone a little further. We've learned some new pathways that we just couldn't talk about when we were making those notes at the time. All right. So we'll, let's see. We'll go Roman numeral number 2. This is going to be alkyne prep. And so we're just going to learn one way to prepare alkynes. So we're going to actually prepare it from alkene. So if we have an alkene, so we'll make it this cis alkene. What we're able to do is treat it with bromine. All right, and so this is, the reason that I saved alkynes for last is because really alkynes are going to mirror the reactivity of alkenes. So we've seen that we can treat an alkene, we can treat an alkene with something like Br2, and so a lot of the reactivity of the alkynes are going to be the same. All right, so what kind of reaction is this? All right, so we have to think back to our list of 9 or 10 reactions that we did. This one would be on there. And so this is a halogenation. And so does a halogenation proceed with syn or anti-stereochemistry? Yeah, it's anti-stereochemistry, which is pretty important. There are a lot of people just coming in and out at 10 o'clock, so I don't know. I guess that's a thing. I don't know if it's a bathroom break or what, but all right. I mean, I don't know what you're drinking. So what we end up is with this anti-bromination, and so we can see that our bromines have added anti, and so we end up with this compound. All right, so that's fine. We've done this before. This is absolutely not a new step that we've just learned. But we know a little bit more. And so now what we're able to do is we're able to take this dibrominated alkane, and we're going to be able to treat it with one equivalent of NaNH2. And so really, we're going to be using this a lot as a strong base. So get used to the sodium NH2. It's a strong base. Conjugate has a pK around 36. And so when we treat this dibromoalkane with a strong base, what reaction do we know could take place? Yeah, and so what we've got is we've got some secondary alkyl halides, right? So here we've got a secondary alkyl halide, and here we've got a secondary alkyl halide. So we ask ourselves, is it a strong base? We say yes, and because it is a strong base, what reaction do we do? Yeah, we do E2. And so let's see, which two do we want to eliminate? Let's make this as clear as possible. Let's eliminate this hydrogen and this bromine. Now the way that I've shown it, are those anticoplanar?
No.
They are not, but could they rotate to be anticoplanar?
Yes.
Sure, we could undergo single bond rotation and have that take place. So assuming that we do that and we line up our configuration correctly, what we're going to end up with is an alkene. And so we've done this before, so this is in your notes. So we can get this alkene. It's going to have this configuration right here. So basically we started with an alkene, we brominated it to form an alkane, and then we eliminated HBr to reform a new different alkene. Alright, so this is our new reaction step right here. Is because when we look at this bromine and this hydrogen, would you say that those are anticoplanar?
Yes.
Yeah, because let's think about it. We've got our bromine that's going out on the right towards you, and then we've got our hydrogen going back away from you, and certainly these things are pointing apart from each other. We've never done an elimination at an sp2 hybridized carbon, but this is going to be the one case where we're able to. And so you can see when the bromine and the hydrogen are trans to each other, we are able to do E2 with an sp2 carbon leaving group bond. All right, so that's going to be really useful. So what we're going to do is we're going to add a second equivalent. So we'll say one more equivalent of our strong base. So what that's going to do is we'll go over here, we'll deprotonate, and we'll do this kind of mechanism. And so what we'll end up with Yep. And so what we'll do is we'll end up with this alkyne right here. All right, so we've been able to start at an alkene and do some transformation such that we're able to end up with an alkyne. So that's all we're really going to worry about. And so you see that I'm talking about one equivalent of reactant here and then one equivalent here. What you could also see is you could see this written as excess base. And so basically, if you have excess base, that just means that you have enough base to keep reacting until you just can't do any more reactivity. So if we have one equivalent of our base, we're only going to be able to do this reaction once. But if we have excess base, meaning that in this case we have at least 2 equivalents of base, and a lot of reactions are done like this. You'll put like 100 equivalents of base in there and make sure that this thing goes all the way to the end. And so in that case, we have excess base, and so we'll go through this intermediate, but we'll just keep going. There's enough base that we're never going to run out. All right, so that's how we prepare some alkynes. Let's see. All right, so the next one's pretty good. This is going to be very useful for the exam. So we're going to call this alkyne reductions. And so again, this is going to be fairly similar to the reductions of an alkene. We've seen that we can take an alkene, we can react it with something like palladium metal on carbon with some hydrogen gas, and so we can end up with the alkane. So we ask ourselves, what happens if we start with an alkyne and we do the same thing? And so we're going to have hydrogen gas, and so we'll use the most common catalyst, which is palladium on carbon. And so what we're going to find results is full reduction of that triple bond all the way down to a single bond. And so we end up with just the alkane like this. All right, so mechanistically, how does that work? Let's think back to our palladium on carbon hydrogen reduction. Is that a cis or is that a syn or an anti-addition? It was syn. Remember, we had our hydrogen that basically would be on this flat catalyst, and then our molecule would line up, and the hydrogens would both add from the bottom. And so that's going to be a syn addition. So what we're going to do to go from our alkyne to our alkane is we're first going to go through an intermediate where we've added some hydrogens to the same side. So we end up with our cis alkene here. And so from there, there's no reason for the reaction to stop. We've got plenty of hydrogen in there and plenty of catalyst. So basically, it's going to be a two-step reaction. It's going to happen very quickly. We'll go from our alkyne to our alkene, and then our alkene to our alkane. And so that's not the most useful thing in the world, because we've already seen that a lot of our transformations take advantage of this alkene functionality. So it'd be nice if we could stop at the alkene, basically pause it so that we can open up lots of different pathways. And so we can ask ourselves, can we stop at the alkene? And so what do you think the answer is? Yes, we most certainly can. So we're going to learn two ways to do that, which can give us either the cis alkene or the trans alkene. And so that is a very, very widely used combination. All right, so first up, the first possibility is going to be that we will use Lindlar's catalyst. All right, and so you might have seen some Lindlar's catalyst on the homework. We haven't learned what it is. And really, I don't care that you know what Lindlar's catalyst is, as long as you can recognize the name and then what it does. Now, what Lindlar's catalyst technically is it's going to be palladium again. It's not palladium on carbon. This time it's going to be palladium on calcium carbonate. And so in addition to the palladium on calcium carbonate, it's also going to have some lead salts. So this is a fairly complex catalyst here. And the lead salts play a pretty pivotal role. What the lead salts do is that they poison the catalyst such that it is less reactive and in fact won't react with alkenes. And so if our catalyst won't react with alkenes, that means once we get to that first intermediate right here, the reaction's done. When we stop it, that's all we'll have in our pot. And so let's see. Furthermore, we just want to make sure we remember that since we're doing a catalyst with H2, it will undergo a syn addition. And so let's see what that looks like. So what we've got is we've got our alkyne. Looks something like this. And so if you see an example that says, all right, we're going to treat it with H2, and furthermore, we're going to treat it with Lindlar's catalyst, we know that we're going to end up doing a syn addition. So we get this product, but that's it. It doesn't keep reducing, and so we could then do one of our mini electrophilic addition reactions that we've learned on that thing. Importantly, we will only have the cis alkene, because mechanistically, we know that this reaction is specific, it's stereospecific. Everything, the hydrogens have to add to the same side, and so we always see the syn addition having happened, and so we get the cis product. All right, so that's a way to get the cis. Number two what we can do is we can use sodium, and this is going to look very very similar to something we've seen before. So let's go ahead and clarify this now. So this right here is sodium metal and ammonia. All right, so we can see two things that look very similar. We can have sodium metal and ammonia, or we can see what looks very similar to that, our NaNH2. And so here, we know we've got a strong base. Over here, this is going to be a reducing agent. So don't get these two things mixed up. This is literally, here we've got a salt. Here we've actually got just a sodium metal sitting in ammonia. And so they're going to do two very different things to our alkyne. All right, so if we obtained our cis only in the first type of reactivity, what do you think we are going to obtain in the second? Trans or cis? Is going to be trans. Another way to get cis wouldn't be very useful. So in this case, we're going to have a way that we can obtain our trans alkene. So for example, we can take, again, our alkyne. So we can treat that thing with sodium and ammonia. So what we'll end up with will be our trans alkene. And so that is useful. Okay, so good for us. We have two ways to basically reduce an alkyne to an alkene now, and so we can make sure that we get either just the cis alkene or the trans alkene. So that'll be cis reductions and trans reductions. We're going to do, we'll probably have time for, let's see. Let's go into Roman numeral 4. I at least want to get you to what we got in the 10 o'clock section. And so we'll call this reactions of alkynes. And our reactions of our alkynes are truly going to be very similar to the reactions of alkenes. And so that's kind of why I've saved this stuff for last, because you've seen it. It's honestly a pretty good review of things you'll need to know on the exam. So the first one we'll take a look at will be the addition of HX. And so when we added HX to an alkene, what kind of regioselectivity did we see? I think I heard it. So in this case, we will still follow Markovnikov's rule. Don't forget about old Markovnikov. Markovnikov would love to mess up your final, so let's make sure we're all very familiar with them. And so, for example, let's just show what it looks like. It's the easiest way. The mechanism is going to be very similar to what we've already done with our alkene. And so let's say we've got, let's use HBr. No, let's use HCl. Let's get away from the bromines for a while. All right, so what's the first step of this mechanism going to be? It's going to be protonation, just the same exact first step as when we added our HB or our HX to an alkene. So we'll start with our electron density of the alkyne, and we'll protonate it. And so let's make one change to our starting material. Instead of having a symmetrical starting material, let's change that ethyl group on the right side. Let's just change it to a hydrogen so that we've got a terminal alkyne and we can see regioselectivity. All right, so we've got two possibilities. We can add our hydrogen to the left side. And so if we add it to the left side, we're going to end up with this carbocation. Or we could add it to the right side. So if we do that, we end up with that carbocation. So which is going to be the more stable carbocation? Top or bottom? Definitely bottom, right? So if we have a secondary carbocation, that's going to be more stable than a primary carbocation. And so just like with the electrophilic additions of alkenes, we're not even going to worry about this top intermediate. We don't say that there's a minor product. We say that this thing is regioselective. It follows Markovnikov's rule. And so from here, we know that we've got, I guess it's not Br, now it's Cl in solution. And so we'll just snap these two guys together such that we end up with this molecule right here. All right, so from there, let's say that we really, what we had done is we had treated this with an excess of HCl. All right, so we didn't really clarify how much HCl we put in there, and so let's say that we had an excess, meaning if we have more HCl remaining in our solution, are these two things going to want to react with each other? Yeah, absolutely. We have an alkene, we have a strong acid, and so this is just stuff we've done before. So again, we're going to do the same mechanism. Will the proton go on the left side or the right side? So if it adds to the right side, we'll end up again with our secondary carbocation. So that's what we see. So we'll add our proton to it. And again, this is just a review of what we've done. So then we have chlorine. So our chlorine will just add in again to our carbocation. And so what we end up with, we don't have to worry about stereochemistry, there isn't any. So we end up with basically this compound right here when we have excess. And so this shouldn't be too surprising. When we have an alkene, we can add HCl to it once. When we have an alkyne, we can add HCl to it twice. And so the difference is that now we end up with two chlorines on our product instead of just the one. You guys are actually much quieter than 10 o'clock. They were pretty rowdy. And a lot of people kept getting up and going to the bathroom. I mean, it was like every 30 seconds someone would be coming in and out of the room. I don't think they were in my class. All right. I shouldn't have said anything. We're going to do 2 more reactions. That's it. All right, so and again, this is stuff that we've already done. So this is going to be the hydration reaction. Woo. It's okay. It's all right. Yeah. All right, so this is going to be the addition of H2O. And so we've done this before with alkenes. If you remember, we did it with catalytic acid and water, or we can do an oxymercuration reduction to do the same thing. And so one thing that's different, a slight difference, is going to be that we can't use catalytic acid with alkynes. So that kind of rules out our catalytic acid water pathway. And so the reason for that is that alkynes, they can do more stuff than alkenes. And so in reality, what happens if you have a lot of alkyne in solution and you put acid in there, you'll typically undergo some polymerization processes. So you'll make big, long, plastic-y type polymers, and so you're not going to do what we're trying to do. So we can't use HA with alkynes, and so instead, what we want to make sure we're doing is just using our oxymercuration pathway. So that was mercury acetate with H2O. So again, we've done this reaction, so we'll work our way through it here. What we're going to find is it works just like with the reaction with the alkene, but we end up with a different product. So that's going to be a little bit of a new concept. That'll kind of be it. That'll be the last concept we learn for orgo. Yeah, yeah. All right. So let's start with our alkyne. All right. So and again, let's make this an asymmetric alkyne. So let's make this right side a proton. All right, so we've got terminal alkyne. Everybody totally remembers the oxymercuration mechanism, right? Yep. We should. That will be testable on the final. All right, so we're going to work our way through it as a reminder. So we've got our mercury acetate that looks like that, and of course our mercury has some lone pairs. And so what's the first step? Yeah, you start with an arrow where? Electrons. Yeah, electrons of your alkyne. Thank you. All right, electrons of the alkyne, and so you may not totally remember this, but an oxymercuration goes through a 3-membered polonium type intermediate. And so what we're going to end up with is going to be this cycloalkene ring. That looks like that. All right, so that shouldn't be totally foreign to you. That's something we've seen in the reactivity with an alkene. Thank you. Yeah, I don't know why I keep trying to make that an ethyl. I did it at 10 o'clock too. All right, so we're gonna have water, and so the next step is attack of water onto one of those carbons. Now, which carbon is going to be attacked? The left one or the right one? And so we're going to do the same line of thinking as we did before. We want to ask ourselves, which carbon would be the more stable carbocation? It'd be the left one. And so what we end up with is some partial positive charge on that left carbon. So that means that we're going to see reactivity at that left carbon, meaning that we will end up with what is ultimately going to be an anti-addition. So that makes sense. Anytime we go through a three-membered ring, we end up with an anti-addition. All right, so we've got that compound. How do we get this to a neutral compound? Yeah, so we want to deprotonate with a base. So that can certainly take place. All right, so when we deprotonate, we're going to end up with this compound. Now, do you think we want mercury left over on our compound?
No.
No, we do not. So what we're going to do, before we had to use like a sodium borohydride workup. In this case, this is even less stable. And so the water that's already in there will actually go ahead and do your workup. We don't care about the mechanism, so we'll say don't worry about the mechanism here. All you need to know is that you're going to end up with this alcohol right here. So basically your mercury will get swapped out with a hydrogen and you get your product. Okay, so I kind of lied. This is not the product you actually recover. And so let's think about why that would be the case. Let's. All right, so let's see. We have an alkene. And then we also have an alcohol next to it. So specifically in cases where we have an alcohol directly attached to an alkene, we're going to call this a special thing. Do you have any idea? All right, so we're going to call this an enol, right? So we can see where that comes from, an ene from the alkene, ol from the alcohol. And so we call this an enol, and so importantly, an enol is not stable. All right, and so what's going to happen is the enol is going to undergo a rapid equilibrium. And so this is going to be an equilibrium that we say favors the other thing. So you can see that our equilibrium arrows are clearly indicating that the equilibrium lies far to the left. So once we form our enol, we're going to undergo what we refer to as ketoenol tautomerization. I know, it's a big one. All right, so ketoenol tautomerization. And so if the right side of this thing is an enol, what do you think the left side is? What has keto in it? What does that sound like? Sounds like a ketone, and that's exactly what we get. So what we actually end up recovering is going to be the constitutional isomer of this compound that is actually an enol. And so we see the reactivity saying we no longer have an alkene. That bond basically moves to here, where this proton moves over to here. And so this actually happens. It's called ketoenol tautomerization. And so importantly, let's go ahead and just define what a tautomer is. So a tautomer is going to be a constitutional isomer that is in rapid equilibrium with another constitutional isomer. So basically, they're constitutional isomers, and typically we say, well, those things are different molecules, but there are special cases where there is a direct equilibrium between constitutional isomers, and so we call those tautomers of each other. And so we don't worry about the mechanism up here. You'll learn that in order 2 if you're taking it. It's there's a couple of different pathways, but we'll just leave it at that. So when you hydrate an alkyne, you do form an alcohol, but that quickly tautomerizes such that we're able to form a ketone. So good for us. We made a ketone. All right, so now we'll do one more relatively quickly, and we'll call it a day. So this will be number 3. And so we've seen hydroboration before, and so we're just going to do it again. There is one small difference in hydroboration of alkynes, and so we're not able to use BH3. So what instead of BH3, we must use, and so I think it's a disec-isoamyl borohydride, something like that. So it is SiA2BH. And so the important thing here is you treat it the same. You don't have to worry about the SiA part. You're going to treat this as a BH bond. What this ultimately looks like is this right here. So that's disec-isoamyl borohydride. And you don't need to be responsible for the structure. What you do need to know, which it should be pretty evident, this is pretty bulky. And that's ultimately why we've got to use it. We've got to use a relatively bulky borohydride when we're doing this reaction. All right, so let's do an example and call it good. All right, so for example, let's say we have this terminal alkyne. And so we know as a secondary carbon, this is going to have a partial positive. This will have a partial negative. So we're going to line up our borohydride in the same exact way. So what we're going to have is our hydrogen on the bottom left and our boron stuff on the right. And so we do that because if you think back to electronegativities, we know that our hydrogen is actually a little more electronegative, so it gets the partial negative. Then we're just lining our stuff up. We're matching up our partial charges just like we did with alkenes. So we line it up this way. And so mechanistically, the same thing will happen. And so what we get after this first step is this compound right here. And so ultimately, this is why we have to use the big, bulky borohydride. It's because once we get to this alkene, we know that alkenes will also react with BH3, right? And so if we just had BH3 here, what we could end up doing is another reaction such that we ended up with 2 borons off of this position. But because we're using a massive, bulky boron hydride reagent here, this will only happen once. So we have to use a big one to prevent further reactivity. So the oxidation workup, as a reminder, is hydrogen peroxide and sodium hydroxide. And so what that leads to is this compound. And so what kind of compound is that? Right next to an alkene, which makes it an enol. Are enols stable? They're not stable, and so we're going to undergo tautomerization. It's going to favor the keto tautomer. And in fact, we don't actually form a ketone in this case. We still form a carbonyl, but what kind of functional group is that? Yeah, that's an aldehyde. So now we have a way that we can form an aldehyde. And so ultimately, we end up forming an aldehyde in this case because we add our oxygen to the less substituted carbon. And so the regioselectivity of hydroboration is anti-Markovnikov. The only one we've really learned, well, I guess we learned some radical stuff. It's also anti-Markovnikov. All right, so now that's our anti-Markovnikov hydroboration. And so we are done. Yeah. Okay, Okay, so let's chat for a minute. So it's been a great semester for me. I know you guys have been working your asses off. It's shown on how you've done on the exams. Yeah, the average dropped on the third one, but it was a tough exam, and for the most part, I think people have done really well, and I know you've been working hard. So first off, give yourselves a round of applause for being awesome this I don't know, it must be a little chilly in here. Okay, so if you've had my class before, and let me just, before I get to that part, I just want to say that it's been an absolute joy being your professor this semester. I took this exact class in this exact room in the spring of 2006. And so that was exactly a decade ago, so I've been in your shoes, and now I'm up here, and it's a lot of fun up here. Maybe not as fun, but I don't remember it as being as much fun on that side. But it is a lot of fun for me, and so if you've been in my class before, you know I like to take a class picture on the last day. And so with Chem, we had about 120 people, and it was very, very crowded. And so we made it work with 10 a.m. You're just going to have to get creative. If some of you have to be on top of things, you figure it out. But we've got someone to take the picture. So just crowd around, tall people in the back, etc. You know, picture rules.
I sent the door.
Alright, there's gonna have to be some kneelers. We might need multiple rows of kneelers. We might even need some kneelers on this row. I don't know, but this basically there's a lot of people. Just keep crowding in. Get uncomfortably close.
She get up Good, how are you? Actually, I don't want to be awkward. Yeah. I know, right?
We've still got like 25 people.
People need to go. Let's go to the backpack.
Yeah, I'm going to be somewhere.
Are you good? Yeah. Most of the bathrooms are good. Thank you.
Alright, we're getting really close. Just keep stretching into this flexible model.
I don't need to be in it. So I come back.
Alright, we're getting really close. Okay, is that yeah, solid? Yeah. Okay, I gotta come down. Okay, alright, I can yell. Alright, take a bunch of pictures. Yay, or go. It's really slow. It's hard to do. Right now you're good. Alright, just take like a couple more.
Yeah.
It's slow.
And then it stops. Yeah. Hold on. I have to turn it on and off to take a photo. Yeah. Funding. Woo.
Alright, that's really good. Thank you so much.
I did. That's really sad.
Where are you going?
Where's
What? The what? I was here. No, I was at the end. Write a note on this thing. I did that last semester. I don't. Oh, the pen's right there.
Should I just meet you down by your office in a couple minutes, or whenever you're
We're
good?
gonna do it in 2018. So
Okay.
it's a conference room upstairs. Just meet me up there.
Is that by the not the
So you know where
library?
the reading room is? At the end of the hallway?
Yep.
It's basically the room right above it. So
All right,
on the second
great.
floor, just right above that.
Sounds good.
I know.
Thank you
It's
so
so
much.
tough. I should have took the board off. I didn't think about that. Oh, you know what I should do in the future? Is I should write like a background of some kind on there, and then that's perfect.
I think it's good though. You can see it.
Yeah.
Picture come out okay?
Yeah, I think it's good. Huh?
You're
I felt them a little bit. I thought that there might be some going on. So, yeah.
There were several.
Yeah, I thought that was the case.
Thank you, Professor Walker.
You're welcome, Becca.
So, I want to talk to you about the exam.
Okay.
So, when I talked to you in your office, I moved it to Wednesday afternoon, I think.
Okay.
Would it be possible to move it to Thursday instead?
Yeah, just email me.
So it would be, okay. I just wanted to, like, see.
Yeah. No, that's totally fine. Thank you. All right, see you guys. Yeah, you're welcome. Oh, we didn't blow up the other balloon, did we? We didn't. Shoot. Yeah, you can absolutely blow it up. Hold on. Oh gosh, no one reminded me. Where are matches? Never gets old. I should have done it more this semester. Yeah. God, we blew so much stuff up last semester. Alright, here you go. For the you might want to cover your ears if you're not expecting. Nice. Alright, there you go.